Tonight, as you settle into the quiet comfort of your evening, I want you to imagine something extraordinary happening right beneath your awareness. While you rest, while you breathe, while your thoughts drift towards sleep, an invisible force is gently pulling at every molecule of water on our planet. It's reaching across 240,000 miles of empty space, tugging at our oceans with a persistence that has never faltered, not once, in the entire history of our world. This force doesn't announce itself with thunder or lightning. It doesn't shake the ground beneath our feet or paint colors across the sky. Instead, it works in whispers, in the slow rhythmic breathing of the sea itself. Twice each day, it draws billions upon billions of gallons of water toward itself, then releases them back again in an eternal dance that has shaped coastlines, guided ancient navigators, and continues to pulse through the very rhythm of life on Earth. You've seen this phenomenon countless times. Perhaps you've walked along a beach at low tide, marveling at the exposed sand stretching far beyond where waves normally reach. Maybe you've returned hours later to find that same sand completely submerged, the water now lapping at rocks and seawalls that were high and dry just moments before. You've witnessed one of the most fundamental forces shaping our planet. Yet most of us never pause to consider the elegant mechanics behind this daily miracle. The moon, our constant celestial companion, is conducting an orchestra of water that spans the entire globe. But how? How can something so distant, something you can cover with your thumb when you hold it up to the night sky, command such power over our vast oceans? How does it reach across the vacuum of space to move trillions of gallons of water with mathematical precision? Tonight, we're going to unravel this mystery together. We'll explore how gravity becomes poetry, how distance transforms into rhythm, and how the same force that keeps your feet planted firmly on the ground reaches out to embrace our planet in ways both subtle and profound. This isn't just a story about water moving up and down. It's a story about connection across impossible distances, about forces so gentle yet so persistent that they've been shaping our world since before life itself emerged from those very waters. If you find comfort in these gentle explorations of our natural world, I'd be grateful if you'd consider subscribing and liking this video. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination flow with the tides themselves. Also, I'd love to know where you're listening from tonight. Comment your time and location below. The story begins, as so many cosmic stories do, with gravity. But not gravity as we typically think of it. Not the gravity that makes apples fall from trees or keeps us anchored to Earth's surface. Instead, we're talking about gravity as a conversation between worlds, a constant dialogue spoken in the language of attraction across the vast emptiness of space. Every object with mass, from the smallest pebble to the largest galaxy, creates what we call a gravitational field. Think of this field as an invisible net stretched through space, with the object sitting at its center like a bowling ball placed on a trampoline. The more massive the object, the deeper it sinks into this cosmic fabric, and the stronger its gravitational pull becomes. Earth, with its tremendous mass of nearly 6 trillion kilograms, creates a powerful gravitational field that extends far beyond our atmosphere. This field reaches out through space, growing weaker with distance, but never completely disappearing. It's what keeps our moon in orbit, what guides the paths of satellites, what shapes the very architecture of our local corner of the universe. But here's where the story becomes truly fascinating. The moon, despite being much smaller than Earth, possesses its own gravitational field. And that field, though weaker than Earth's, reaches across the 250,000 miles between us to tug gently but persistently at everything on our planet's surface, including our oceans. Now, you might wonder why we feel the moon's gravitational pull most dramatically in our oceans rather than, say, in our lakes or rivers or even in our own bodies. The answer lies in something beautifully simple yet profound: water's ability to flow. The gravitational force the moon exerts on Earth is actually quite weak compared to Earth's own gravity. It's roughly 10 million times weaker, in fact. But water, unlike solid rock or even the gases in our atmosphere, can respond to even the gentlest persistent force by moving, by flowing, by reshaping itself across vast distances and timescales. Imagine trying to pull a mountain toward you with a piece of thread. The mountain won't budge because its structure is rigid, locked in place by the immense forces holding rock and stone together. But imagine that same thread pulling on a vast puddle of honey. Given enough time, given enough persistence, that honey will begin to flow in the direction of the pull. The ocean is like that honey, fluid enough to respond to forces that solid matter simply cannot. But the moon's influence on our tides involves more than just a simple pull. The real magic happens because of something called the tidal force. And understanding this force requires us to think about gravity in a way that might seem counterintuitive at first. Here's the key insight. The moon doesn't pull on Earth as a single, solid object. Instead, it pulls differently on different parts of our planet depending on how close those parts are to the moon at any given moment. The side of Earth facing the moon experiences a stronger gravitational pull than Earth's center, which in turn experiences a stronger pull than the side facing away from the moon. This difference in gravitational strength across Earth's diameter is what creates the tidal force. It's not that the moon is simply pulling water toward itself, though that's part of the story. Rather, the moon is stretching Earth slightly, creating a gradient of gravitational attraction that causes water to flow toward the points of strongest and weakest pull. Picture Earth as a slightly flexible ball being gently squeezed and stretched by invisible hands. The water on our planet's surface responds to this stretching by flowing toward the areas where the gravitational gradient is steepest. This creates not one bulge of water pointing toward the moon, as you might expect, but two bulges on opposite sides of our planet. The bulge on the side facing the moon forms because water there experiences the strongest lunar gravitational pull. But surprisingly, another bulge forms on the exact opposite side of Earth, the side facing away from the moon. This happens because that distant water experiences the weakest lunar pull, allowing Earth's own rotation to fling it slightly outward while the moon tugs more strongly on the planet's center. These two bulges of water, one reaching toward the moon and one reaching away from it, travel around our planet as Earth rotates on its axis. As our planet spins once every 24 hours, different coastlines pass through these bulges, experiencing high tide as they encounter the elevated water levels and low tide as they pass through the areas between the bulges. But the moon adds another layer of complexity to this dance because it's not standing still in space. While Earth rotates on its axis once every 24 hours, the moon is simultaneously orbiting around Earth once every 27 1/3 days. This means the moon is constantly changing position relative to any fixed point on Earth's surface. From the perspective of someone standing on a beach, the moon appears to rise about 50 minutes later each night. This happens because as Earth completes one full rotation, the moon has moved slightly further along in its orbit, requiring Earth to rotate a bit more to catch up. This 50-minute delay means that high tides also arrive about 50 minutes later each day, creating a tidal rhythm that doesn't quite match our solar day, but instead follows what oceanographers call the lunar day. The result is a complex but predictable pattern. Most coastal locations experience 2 high tides and 2 low tides, approximately every 24 hours and 50 minutes. The timing shifts gradually, so a high tide that occurs at noon today will occur around 12:50 tomorrow, then around 1:40 the day after that, and so on. This predictable rhythm has guided human civilization for millennia. Ancient navigators learned to read the tides like a cosmic clock, timing their departures and arrivals to take advantage of the deeper waters of high tide, or the exposed channels and sandbars revealed at low tide. Coastal communities built their lives around this rhythm, scheduling fishing expeditions, gathering expeditions, and even social gatherings to align with the moon's influence on their shores. But the moon's effect on our tides is far from uniform across the globe. The actual height and timing of tides at any specific location depend on a fascinating interplay of factors that transform the moon's simple gravitational pull into an infinitely complex symphony of moving water. The shape of ocean basins plays a crucial role in determining how tidal forces manifest at different coastlines. Wide, deep ocean basins allow tidal bulges to move relatively freely, while narrow channels and shallow areas can amplify or diminish tidal effects dramatically. The Bay of Fundy, stretching between Nova Scotia and New Brunswick, experiences some of the highest tides in the world, with water levels changing by more than 50 feet between high and low tide. This extreme range occurs because the bay's funnel shape and depth create a resonance effect that amplifies the moon's tidal influence. Conversely, some bodies of water show almost no tidal variation at all. The Mediterranean Sea, despite its size, experiences tides of only a few inches in most locations because its narrow connection to the Atlantic Ocean prevents the full tidal bulge from entering and circulating freely. The depth and contour of the ocean floor also influence how tidal waves propagate across ocean basins. These tidal waves, quite different from the surface waves we see crashing on beaches, are massive movements of water that can travel thousands of miles across ocean basins. They move fastest in deep water and slow down as they approach shallow coastal areas, much like a massive, invisible tsunami that arrives twice each day with clockwork regularity. Continental shelves, underwater mountain ranges, and deep ocean trenches all affect the speed and direction of these tidal waves, creating complex patterns of interference where tidal waves from different parts of an ocean basin meet and either reinforce or cancel each other out. Islands and coastlines with complex geometries can create particularly intricate tidal patterns. Archipelagos like those found in the Pacific Northwest or the coast of Maine experience tidal effects that vary dramatically over short distances as tidal waves navigate between islands, around headlands, and up into narrow inlets and bays. The rotation of Earth itself adds another layer of complexity through what's known as the Coriolis effect. This effect, caused by Earth's rotation, tends to deflect moving objects to the right in the northern hemisphere and to the left in the southern hemisphere. For tidal waters, this means that tidal currents don't simply flow directly toward and away from the moon's position, but instead follow curved paths that spiral around ocean basins. These rotating tidal currents create what oceanographers call amphidromic points, locations in the ocean where there is virtually no tidal rise and fall at all. Instead, the tide rotates around these points like water swirling around a drain, completing one full rotation every 12 hours and 25 minutes. Understanding these amphidromic systems is crucial for predicting tides accurately across entire ocean basins. Weather patterns can also influence tidal behavior, though they don't change the fundamental gravitational forces at work. Strong onshore winds can push water toward the coast. Making winds can have the opposite effect. Higher, while offshore high tides Even atmospheric pressure changes associated with weather systems can also cause water levels to rise or fall slightly, adding or subtracting from the moon's gravitational influence. Storm surges, those dangerous elevations in sea level that accompany hurricanes and other severe storms, often become most destructive when they coincide with naturally occurring high tides. The combination of the moon's gravitational pull and meteorological forces can create water levels far higher than either factor could produce alone. Human activities have also begun to influence tidal patterns in some locations. Large dams that restrict river flow can affect tidal ranges in estuaries and bays. Dredging operations that deepen channels can change how tidal waves propagate inland. Even massive construction projects like land reclamation can alter local tidal patterns by changing the shape and volume of coastal waters. Despite all these complicating factors, the fundamental rhythm established by the moon's gravitational influence remains remarkably consistent and predictable. Tidal prediction has become one of the most precise branches of applied astronomy, with computers able to calculate into tidal heights and times years the future with extraordinary accuracy. This predictability exists because, beneath all the local variations and complications, the moon's gravitational influence follows the same mathematical principles that govern all celestial mechanics. The same equations that allow us to predict planetary orbits and spacecraft trajectories also enable us to forecast exactly when high tide will occur at any given location, months or even years in advance. Yet even as we've mastered the mathematics of tidal prediction, the actual experience of witnessing tides remains one of nature's most meditative and awe-inspiring phenomena. Standing on a beach and watching the slow, inexorable advance or retreat of the waterline connects us directly to forces operating on cosmic scales, reminding us that our planet exists not in isolation, but as part of a dynamic gravitational dance with our celestial companion. The rhythm of the tides serves as a bridge between human timescales and cosmic timescales, between the immediate and the eternal. In the space of a few hours, we can witness the results of gravitational forces that have been shaping our planet for billions of years, forces that will continue long after human civilization has become just another layer in Earth's geological record. This predictable cosmic rhythm has woven itself into the very fabric of life on Earth in ways both obvious and profoundly subtle. The earliest life forms that emerged from the primordial oceans billions of years ago developed their biological clocks in synchronization with these tidal cycles. Even today, countless species across our planet still march to the beat of the lunar drum. Their behaviors and life cycles intimately connected to the ebb and flow of tidal waters. Consider the remarkable Grunion fish of California's coast, whose entire reproductive strategy revolves around the highest tides of each month. These small, silvery fish time their spawning runs to coincide with the spring tides that occur during full and new moons, when tidal ranges reach their peak. On warm summer nights, thousands of Grunion ride the waves onto sandy beaches, the females burying their eggs in the sand just above the high tide line, while males release clouds of fertilizing milt into the retreating waters. The timing is exquisite in its precision. The eggs incubate safely in the moist sand for exactly 2 weeks, protected from predators and ocean currents. Then, as the next cycle of spring tides arrives, the rising waters wash over the nesting sites, triggering the eggs to hatch instantly. The newborn fish are swept out to sea by the very same tidal forces that brought their parents to shore. Across the globe, similar stories unfold wherever land meets sea. Fiddler crabs emerge from their burrows in perfect synchronization with low tide. scurrying across exposed mudflats to feed on organic matter revealed by the receding waters. Their internal clocks are so precisely tuned to tidal cycles that researchers have found they maintain their rhythmic activity patterns even when removed from coastal environments and placed in laboratory settings far from any ocean influence. Sea turtles, those ancient mariners of the ocean, depend on tidal cycles for some of their most critical life events. Female sea turtles often time their nesting activities to coincide with high tides, using the elevated water levels to access beaches that would otherwise be unreachable. The hatchlings, emerging weeks later, instinctively wait for the cover of darkness and the assistance of high tide to begin their perilous journey from nest to ocean. Even microscopic organisms participate in this grand tidal symphony. Certain species of marine algae release their reproductive cells in coordination with tidal cycles, ensuring optimal dispersal and fertilization rates. These tiny organisms, invisible to the naked eye, somehow sense and respond to the same gravitational forces that move vast ocean basins. But the moon's influence extends far beyond the behaviors of individual species. Entire ecosystems pulse with tidal rhythms, creating dynamic environments that shift dramatically between high and low tide conditions. Intertidal zones, those narrow strips of coastline that exist between the highest and lowest tide marks, represent some of the most challenging and diverse habitats on our planet. Twice each day, these ecosystems transform from terrestrial to marine environments and back again. The creatures that call these zones home must survive being alternately submerged in salt water and exposed to air, sun, and wind. They must endure temperature fluctuations, changes in salinity, and the mechanical stress of crashing waves followed by periods of complete stillness. The zonation patterns you observe when walking across a rocky intertidal area at low tide reflect millions of years of evolutionary adaptation to these tidal rhythms. Barnacles cluster in the highest zones, their cone-shaped shells designed to retain moisture during long periods of exposure. Below them, mussels form dense beds in areas that experience moderate tidal coverage. Their strong attachment threads allowing them to withstand powerful wave action, while their ability to seal their shells tightly helps them survive exposure to air. Lower still, in pools that retain water even at the lowest tides, sea anemones unfurl their tentacles like underwater flowers, creating miniature ecosystems that serve as refuges for small fish, crabs, and other marine creatures during low tide periods. Each zone represents a different compromise between the opportunities and challenges presented by tidal cycles. The productivity of these intertidal ecosystems rivals that of tropical rainforests, largely because tidal action continuously brings fresh nutrients and oxygen while removing waste products. The constant mixing and circulation created by tidal currents prevents stagnation and maintains the chemical conditions necessary for robust marine life. Tidal pools, those temporary windows into marine ecosystems revealed at low tide, offer glimpses into evolutionary laboratories where species continuously adapt to rapidly changing conditions. The creatures in these pools must cope with temperature swings that can vary by 20 degrees or more between high and low tide, salinity changes caused by evaporation and rainfall, and oxygen levels that fluctuate dramatically depending on wave action and biological activity. Salt marshes and mangrove forests represent ecosystems entirely shaped by tidal forces. These coastal wetlands experience regular flooding and draining cycles that create unique environmental gradients. Plants in these systems have evolved specialized adaptations for dealing with salt water, including specialized root systems that can filter salt from seawater and leaves that can excrete excess salt through specialized glands. The soil chemistry in these tidal wetlands changes dramatically between high and low tide periods. When flooded, the saturated sediments become anaerobic, supporting completely different microbial communities than when exposed to air during low tide. These alternating conditions create complex biogeochemical cycles that make tidal wetlands among the most productive ecosystems on Earth. The economic value of these tidal ecosystems extends far beyond their ecological importance. Coastal wetlands serve as natural storm barriers, absorbing wave energy and reducing coastal erosion. They act as natural water treatment systems, filtering pollutants and excess nutrients from runoff before it reaches open ocean waters. They serve as nurseries for commercially important fish species, with many marine fish depending on tidal wetlands for critical phases of their life cycles. Oyster reefs, which thrive in tidal environments, provide multiple ecosystem services while supporting major commercial fisheries. The filter feeding activity of oysters helps maintain water quality, with a single oyster capable of filtering up to 50 gallons of water per day. The complex three-dimensional structure of oyster reefs provides habitat for hundreds of other species while protecting coastlines from wave erosion. Human communities have learned to work with tidal rhythms rather than against them, developing technologies and practices that harness tidal energy for practical purposes. Tidal mills, which use the flow of tidal currents to turn water wheels, have operated in coastal areas for over 1,000 years. These mills could grind grain, saw lumber, or power other machinery using the predictable energy provided by rising and falling tides. Modern tidal energy systems represent sophisticated evolutions of these ancient technologies. Tidal barrages, massive dam-like structures built across estuaries, capture the potential energy of high tides and release it through turbines as the tide ebbs. The Rance tidal power station in France, operational since 1966, demonstrates the feasibility of large-scale tidal energy generation, producing enough electricity to power hundreds of thousands of homes. Underwater tidal turbines, resembling submerged wind farms, represent another approach to harvesting tidal energy. These systems can be deployed in areas with strong tidal currents without requiring the massive construction projects associated with tidal barrages. The predictability of tidal cycles makes these systems particularly valuable for electrical grid management, as operators can forecast tidal energy production years in advance. The navigation challenges presented by tidal cycles have driven innovations in maritime technology and coastal engineering for millennia. Ancient harbour designs incorporated tidal considerations, with breakwaters and channel depths calculated to accommodate the full range of tidal conditions. Modern ports continue to rely on tidal predictions for scheduling ship movements, with large vessels often required to wait for high tide conditions to safely navigate shallow channels. Tidal bore phenomena, where incoming tides form actual waves that travel upstream in rivers, create some of the most dramatic expressions of tidal forces. The Amazon River's Pororoca, the Seven Rivers Bore in England, and the Qiantang River's Silver Dragon in China are examples of tidal bores that can travel dozens of miles inland, bringing ocean rhythms deep into continental interiors. These bore waves can reach heights of several meters and travel at speeds exceeding 20 miles per hour, creating natural phenomena that blur the boundaries between river and ocean systems. The formation of tidal bores requires specific combinations of river depth, channel shape, and tidal range, making them relatively rare but spectacular demonstrations of tidal power. The cultural and spiritual significance of tidal rhythms appears in human societies across the globe, suggesting that our connection to these cosmic cycles runs deeper than mere practical considerations. Coastal cultures often organize their calendars, ceremonies, and social activities around tidal cycles. Recognizing the tides as expressions of larger natural rhythms that govern life itself, many indigenous cultures view tidal cycles as manifestations of relationships between celestial and terrestrial forces, incorporating tidal knowledge into complex systems of environmental observation and prediction. These traditional ecological knowledge systems often demonstrate remarkably sophisticated understanding of local tidal patterns, seasonal variations, and the connections between tidal cycles and other natural phenomena. The meditative quality of watching tides has inspired artists, poets, and philosophers throughout human history. The slow, rhythmic advance and retreat of tidal waters offers a natural metronome for contemplation, a reminder of time scales both longer and more fundamental than human concerns. Standing at the edge of the sea during tidal transitions, watching water levels change almost imperceptibly moment by moment, yet dramatically over hours, connects observers to processes operating on cosmic scales. This connection between human consciousness and tidal rhythms may reflect evolutionary adaptations that developed during our species' long association with coastal environments. Some researchers suggest that the approximately 90-minute cycles observed in human sleep patterns may be evolutionary echoes of tidal rhythms, remnants of biological clocks that once synchronized our ancestors' activities with the ebb and flow of coastal waters. The mathematical precision underlying tidal cycles continues to reveal new insights about the gravitational relationships between Earth, Moon, and Sun. Advanced tidal analysis can detect subtle variations in Earth's rotation rate, changes in the Moon's orbital distance, and even the gravitational effects of other planets on our ocean systems. Satellite altimetry, which measures ocean surface heights with centimeter precision, has revolutionized our understanding of global tidal patterns. These measurements reveal how tidal energy propagates across entire ocean basins, creating detailed maps of tidal amplitude and phase that show the planet-scale circulation patterns driven by lunar gravity. Climate change adds new complexity to tidal systems as rising sea levels alter the baseline upon which tidal variations occur. While the fundamental gravitational forces remain unchanged, the practical impacts of tides on coastal communities are shifting as higher baseline water levels mean that storm surges and spring tides reach further inland and cause more frequent flooding. The study of ancient tidal patterns preserved in geological formations provides insights into Earth's deep history and the evolution of the Earth-Moon system. Rhythmites, sedimentary rocks that preserve daily and monthly cycles of tidal deposition, reveal that tidal ranges were much larger in the distant past when the Moon orbited closer to Earth. These geological records suggest that early Earth experienced tides hundreds of feet high, with tidal currents powerful enough to influence global ocean circulation patterns and potentially affect the development of early life. As the Moon gradually moves away from Earth due to tidal friction, these extreme tidal conditions represent a vanished aspect of our planet's history. Yet even as we contemplate these ancient extremes, the tides we experience today continue to weave themselves into the fabric of modern life in ways both obvious and surprisingly subtle. The timing of coastal flights adjusts to accommodate tidal windows that determine runway accessibility on island airstrips. Coastal construction projects must account for tidal schedules that dictate when heavy equipment can access work sites. Even the routing of undersea cables follows tidal considerations, as installation vessels require specific water depth conditions that only occur during certain phases of the tidal cycle. The influence of lunar gravity extends beyond the obvious rise and fall of ocean waters into realms that challenge our intuitive understanding of how celestial forces shape earthly phenomena. Underground aquifers, those vast reservoirs of fresh water trapped in porous rock formations beneath our feet, respond to the same tidal forces that move our oceans. Wells and springs in coastal areas often show measurable fluctuations that mirror tidal patterns. As the moon's gravity gently squeezes and releases the water-bearing rock formations far below the surface, this underground tidal influence can be detected hundreds of miles inland, revealing that the moon's gravitational reach penetrates deep into continental interiors through pathways invisible to surface observation. Hydrologists have learned to account for these lunar effects when measuring groundwater levels and flow rates, recognizing that even our most fundamental water resources participate in the cosmic dance between Earth and its satellite companion. The atmosphere itself, though far less responsive than liquid water, shows subtle tidal variations that meteorologists have only recently learned to detect and measure. Atmospheric tides, driven by the same gravitational forces that move our oceans, create pressure variations so small they're measured in fractions of millibars. These atmospheric oscillations follow complex patterns that combine lunar gravitational effects with solar heating cycles, creating layered rhythms in the very air we breathe. Weather prediction models now incorporate these atmospheric tidal effects, recognizing that they can influence wind patterns, storm development, and precipitation distribution in ways that compound over time. The butterfly effect of chaos theory finds expression in these tiny lunar influences on atmospheric pressure, reminding us that the moon's gravity touches every aspect of Earth's dynamic systems. Even the solid Earth beneath our feet responds to lunar tidal forces, though the response is measured in centimeters rather than meters. Earth tide phenomena cause the ground itself to rise and fall in response to the moon's gravitational pull, with the planet's surface flexing like a slowly breathing chest. This solid Earth tide reaches maximum amplitudes of about 30 centimeters during spring tides, though the effect is distributed over such vast areas that human senses cannot detect it directly. Sensitive scientific instruments can measure these ground movements with extraordinary precision, revealing that the entire planet participates in tidal rhythms. Gravity meters, seismographs, and laser interferometers all detect the subtle ways that lunar gravity reshapes our world twice each day. These measurements have become crucial for calibrating scientific instruments and separating genuine geological signals from the background noise of lunar influence. The global positioning system must account for solid Earth tides to maintain its remarkable accuracy. GPS satellites calculate positions by measuring the time it takes radio signals to travel between satellites and receivers. But these calculations assume that ground-based receivers maintain fixed positions. The centimeter-scale movements caused by Earth tides would introduce unacceptable errors into GPS navigation without sophisticated correction algorithms that predict and compensate for lunar tidal effects. Volcanic activity shows correlations with tidal cycles that suggest the moon's gravity can influence the timing of eruptions and seismic events. The additional stress imposed by tidal forces on magma chambers and fault systems represents a small but potentially significant trigger for geological activity that was already approaching critical thresholds. While tidal forces don't cause earthquakes or volcanic eruptions, they may influence the precise timing of events that were inevitable due to longer-term geological processes. Research into these correlations reveals the interconnected nature of Earth systems, showing how gravitational forces operating on astronomical scales can influence phenomena we typically think of as purely geological. The moon's influence on seismic activity demonstrates that our planet's internal dynamics cannot be completely separated from the celestial mechanics of the Earth-Moon system. Ice sheets and glaciers Those vast repositories of frozen water also respond to tidal forces in ways that are reshaping our understanding of ice dynamics and sea level change. Tidal flexing of ice shelves, particularly in Antarctica, creates stress patterns that influence calving rates and the stability of these massive ice formations. The grounding lines where glaciers transition from land-based ice to floating ice shelves experience tidal pumping that can accelerate ice loss through mechanisms that scientists are still working to understand. These glacial tidal effects have implications for global sea level rise that extend far beyond the direct contribution of melting ice. Changes in ice shelf stability, driven partly by tidal forces, can alter the flow rates of upstream glaciers, potentially affecting ice discharge rates from entire continental ice sheets. Climate scientists now recognize that understanding future sea level rise requires accounting for the complex interactions between lunar tidal forces and ice sheet dynamics. The precision required to predict these interactions has driven the development of increasingly sophisticated computer models that simulate tidal forces across multiple timescales and physical systems simultaneously. These models must account for the gravitational effects of both Moon and Sun, the changing orbital relationships between these bodies, and the complex ways that tidal energy dissipates through friction in ocean basins, solid Earth deformation, and ice sheet dynamics. Ocean circulation patterns on a global scale show the influence of tidal mixing, where tidal currents stir deep ocean waters and bring nutrients from the depths to surface waters. This tidal mixing contributes to the ocean's role as a global heat distribution system, helping to moderate climate by transporting warm water toward polar regions and cold water toward equatorial areas. Without tidal mixing, the oceans would be far less effective at regulating global temperatures, potentially leading to more extreme climate variations. The biological productivity of the oceans depends heavily on this tidal mixing, which brings essential nutrients from deep water to the sunlit surface waters where photosynthesis occurs. Marine food webs ultimately trace their energy sources to this lunar-driven circulation, making the Moon an indirect but crucial contributor to ocean ecosystem health. The timing and intensity of seasonal phytoplankton blooms often correlate with tidal mixing patterns that determine nutrient availability in surface waters. Commercial fishing industries have learned to work with these tidal influences, timing their operations to coincide with tidal conditions that concentrate fish populations or improve fishing success rates. Many fish species show behavioral patterns linked to tidal cycles, with feeding, spawning, and migration activities often synchronized with specific tidal conditions. Understanding these patterns allows fishing operations to optimize their efforts while potentially reducing their environmental impact through more targeted and efficient harvesting strategies. Aquaculture operations, particularly those located in tidal waters, must design their systems to work with, rather than against, tidal forces. Oyster farms, kelp cultivation, and fish pen operations all depend on tidal currents for water quality maintenance, nutrient delivery, and waste removal. The success of these operations often depends on selecting sites where tidal conditions provide optimal flow rates without creating destructive current velocities. The restoration of degraded coastal ecosystems increasingly recognizes the importance of restoring natural tidal patterns that may have been disrupted by human development. Wetland restoration projects focus on re-establishing tidal connections that allow natural flooding and draining cycles to resume. These efforts often require removing or modifying human structures like dikes, tide gates, and channels that have altered natural tidal circulation patterns. Salt pond restoration in San Francisco Bay represents one of the largest tidal restoration projects ever attempted, involving the conversion of thousands of acres of industrial salt ponds back to natural tidal marshes and mudflats. The project requires careful engineering to ensure that restored areas receive appropriate tidal circulation while protecting adjacent developed areas from flooding. Success depends on understanding the complex relationships between tidal flows, sediment transport, and ecosystem development. The acoustic environment of coastal waters shows daily rhythms linked to tidal cycles, as marine life adjusts its vocal behaviors to tidal conditions. Fish, marine mammals, and crustaceans often time their acoustic activities to coincide with tidal states that optimize sound transmission or minimize interference from tidal noise. These patterns create natural soundscapes that pulse with lunar rhythms, adding another sensory dimension to the coastal environment's tidal character. Underwater noise pollution from shipping and industrial activities interacts with these natural acoustic cycles in ways that can disrupt marine communication systems. Understanding tidal influences on underwater acoustics helps researchers and regulators develop strategies for minimizing human noise impacts on marine life by timing noisy activities to avoid critical communication periods for sensitive species. Coastal erosion and sediment transport follow complex patterns influenced by tidal cycles that determine when and where waves can access different parts of the shoreline. The interaction between tidal water levels and wave energy creates erosion patterns that vary dramatically between high and low tide conditions. Understanding these interactions is crucial for coastal engineering projects designed to protect shorelines while maintaining natural sediment transport processes. Beach nourishment projects must account for tidal influences on sediment movement to ensure that added sand remains in desired locations rather than being redistributed by tidal currents. The timing of construction activities often depends on tidal schedules that provide access to work areas, while minimizing environmental disruption during sensitive periods for local wildlife. The emerging field of tidal energy harvesting represents humanity's newest attempt to work with, rather than against, the fundamental forces that shape our coastal environments. Unlike fossil fuel extraction or even solar and wind energy, tidal energy systems operate in harmony with natural rhythms that have persisted for billions of years. The challenge lies in designing systems that can capture useful energy without disrupting the ecological and physical processes that depend on natural tidal flows. Second-generation tidal energy technologies focus on minimizing environmental impacts while maximizing energy capture efficiency. Fish-friendly turbine designs reduce risks to marine life, while advanced materials and engineering techniques improve durability in harsh marine environments. These systems must operate reliably in conditions that combine saltwater corrosion, mechanical stress from tidal currents, and biological fouling from marine organisms. The integration of tidal energy into electrical grids requires sophisticated forecasting systems that can predict energy generation with the same precision used for tidal predictions. Unlike solar and wind energy, which vary unpredictably with weather conditions, tidal energy follows mathematical patterns that can be calculated decades in advance. This predictability makes tidal energy particularly valuable for grid stability and long-term energy planning. Smart grid technologies are being developed to optimize the use of tidal energy by coordinating energy storage and distribution with tidal cycles. Battery systems and other energy storage technologies can capture tidal energy during peak generation periods and release it when tidal generation is low, creating a steady power supply from naturally variable tidal cycles. The global distribution of tidal energy resources reflects the complex geography of ocean basins and coastal configurations that concentrate tidal flows in specific locations. The Bay of Fundy, the Bristol Channel, the Pentland Firth, and other areas with exceptional tidal ranges or current velocities represent premium sites for tidal energy development. However, developing these resources requires balancing energy extraction with protection of the unique ecosystems that have evolved in these high-energy tidal environments. International cooperation in tidal energy development reflects the shared nature of tidal forces that cross political boundaries as easily as they cross ocean basins. Tidal energy projects in one location can potentially affect tidal patterns in neighboring regions, requiring coordination between nations to ensure that energy development doesn't create unintended consequences for coastal communities or ecosystems elsewhere. Term sustainability of tidal energy depends. The long on understanding how energy extraction affects the fundamental tidal processes that drive these systems. Large-scale tidal energy development could theoretically alter tidal patterns if energy extraction reaches levels that significantly reduce tidal current velocities or water level variations. Research into these potential impacts guides the development of sustainable tidal energy policies that protect natural tidal processes while allowing beneficial energy development. As we continue to deepen our understanding of how lunar gravity shapes our world, new applications of tidal knowledge emerge across disciplines ranging from archaeology to space exploration. Archaeological sites in coastal areas often show evidence of past tidal influences that help researchers understand ancient sea levels, coastal configurations, and human settlement patterns. Tidal analysis of geological formations provides insights into Earth's rotation history and the evolution of the Earth-Moon system over geological time. Space agencies study Earth's tidal systems as analogues for understanding tidal forces on other worlds, particularly the moons of Jupiter and Saturn, where tidal heating drives geological activity and potentially maintains subsurface oceans. The principles governing Earth's tides apply throughout the solar system, helping scientists predict and understand tidal phenomena on worlds we may never visit directly. The moon that pulls so gently, yet persistently on our oceans, represents more than just a gravitational influence. It serves as a constant reminder that Earth exists not in isolation, but as part of a dynamic system where celestial mechanics and earthly processes interweave in patterns of extraordinary complexity and beauty. Every tide carries within it the mathematical precision of orbital mechanics, combined with the fluid adaptability of water responding to forces that bridge the gap between astronomical and human scales. Tonight, as you listen to these words, the moon continues its eternal orbit, pulling at the waters of our world with the same patient persistence it has shown for billions of years. The tides it creates connect us to rhythms that began before life itself emerged from the primordial seas. Rhythms that will continue long after human civilization has become just another layer in Earth's geological record. In understanding how the moon moves our tides, we glimpse something profound about the interconnected nature of our universe, where forces operating across vast distances and timescales converge to create the dynamic, ever-changing world we call home. The gentle tug of lunar gravity reminds us that we are part of something much larger than ourselves, participants in a cosmic dance that plays out across the infinite stage of space and time. The story of tidal forces becomes even more intriguing when we consider that Earth is not alone in its gravitational dance with the moon. Our sun, that massive nuclear furnace at the center of our solar system, also exerts its own tidal influence on our planet's waters, though the sun is nearly 400 times farther from Earth than the moon. Its immense mass, over 27 million times greater than our lunar companion, means its gravitational pull still reaches across the void to tug at our oceans. But here's where the mathematics of celestial mechanics reveals something beautiful and counterintuitive. Despite the sun's overwhelming mass advantage, its tidal effect on Earth is only about half as strong as the moon's influence. This happens because tidal forces depend not just on mass, but on distance, and they diminish rapidly as distance increases. The Moon's proximity to Earth more than compensates for its smaller size, making it the dominant conductor in our planet's tidal orchestra. Yet the Sun's gravitational voice cannot be ignored entirely. When the Sun and Moon align their gravitational pulls, working together rather than at cross purposes, they create what oceanographers call spring tides. These enhanced tides occur twice each month, during the new moon when Sun and Moon appear on the same side of Earth, and during the full moon when they pull from opposite sides, but their forces combine constructively. During spring tides, the tidal range increases dramatically. High tides climb higher, low tides drop lower, and the difference between them can exceed normal variations by 50% or more. Coastal communities learn to plan around these enhanced tidal cycles, knowing that spring tides bring both opportunities and challenges that don't exist during normal tidal periods. The term spring tide has nothing to do with the season of spring, but derives from the Old English word meaning to leap or jump, referring to the way water levels seem to leap to unusual heights during these enhanced tidal periods. Ancient observers noticed these patterns long before understanding the gravitational mechanisms behind them, recognizing that certain phases of the Moon consistently brought more extreme tidal conditions. Conversely, when the Sun and Moon work at cross purposes, their gravitational influences partially cancel each other out, creating what are known as neap tides. These occur during the first and third quarter moons, when the Sun and Moon form a right angle as viewed from Earth. During neap tide periods, tidal ranges are minimized, with less dramatic differences between high and low water levels. The cycle between spring and neap tides creates a fortnightly rhythm that overlays the daily pattern of 2 high and 2 low tides. This 14-day cycle from spring tide to neap tide and back again adds another layer of complexity to tidal predictions, creating variations that must be calculated months or years in advance for accurate navigation and coastal planning. But the gravitational influences shaping our tides extend even beyond this Sun-Moon partnership. The other planets in our solar system, though much more distant, possess enough mass to create measurable perturbations in tidal patterns. Venus, when it passes between Earth and the Sun during inferior conjunction, adds its gravitational voice to the solar system's tidal chorus. Jupiter, despite its vast distance, exerts subtle influences that sophisticated tidal analysis can detect and quantify. These planetary influences operate on much longer timescales than the familiar daily and monthly tidal cycles. They create what astronomers call secular variations, gradual changes in tidal patterns that unfold over years, decades, or even centuries. While these variations are too small to notice in daily experience, they demonstrate the truly interconnected nature of gravitational forces operating throughout our solar system. The precision required to account for all these gravitational influences in tidal predictions represents one of humanity's greatest achievements in applied mathematics and astronomy. Modern tidal prediction algorithms must simultaneously calculate the positions and gravitational effects of dozens of celestial bodies, accounting for the elliptical nature of their orbits, the precession of orbital planes, and the complex resonances that arise when multiple periodic forces interact. The mathematical beauty nested cycles reflects deeper truths about the nature of gravitational systems and the way celestial mechanics creates order from apparent chaos. What might seem like random variations in tidal heights and timings actually follows precise mathematical relationships that connect our daily experience of rising and falling waters to the grand clockwork of planetary motion. This mathematical precision has practical implications that extend far beyond academic interest. Modern shipping depends on tidal predictions accurate to within minutes and centimeters for safe navigation of shallow channels and harbor entrances. A miscalculation in tidal timing can ground a massive cargo ship or prevent it from clearing bridge heights, with economic consequences that ripple through global supply chains. Military operations in coastal environments require equally precise tidal intelligence. Amphibious landings must coordinate with tidal conditions that provide appropriate water depths for landing craft, while avoiding periods when extreme low tides would expose troops to enemy fire or strand vessels on exposed beaches. Historical military campaigns, from ancient coastal raids to modern naval operations, have succeeded or failed based partly on commanders' understanding of local tidal conditions. The environmental monitoring networks that track ocean health and climate change rely heavily on accurate tidal predictions to separate genuine environmental signals from the background noise of normal tidal variation. Sea level measurements used to document global warming must account for tidal influences with extraordinary precision to detect the centimetre-scale changes that occur over decades of climate monitoring. Scientific research stations in remote coastal locations often depend entirely on tidal schedules for resupply and personnel transport. Research conducted in places like Antarctica or remote Arctic islands must work within weather windows that align with tidal conditions suitable for aircraft landings on beaches or supply boat access to shallow anchorages. The cultural significance of understanding these complex tidal patterns appears in human societies wherever people have lived close to the sea. Traditional ecological knowledge systems developed by coastal peoples often demonstrate sophisticated understanding of the relationships between lunar phases, seasonal variations, and local tidal patterns that rivals modern scientific predictions in accuracy and detail. Polynesian navigators developed wayfinding techniques that incorporated tidal knowledge alongside star positions and wave patterns to navigate across thousands of miles of open ocean. Their traditional navigation methods required understanding how tidal patterns varied between different island groups, and how seasonal changes affected tidal timing and intensity throughout the Pacific. Celtic and Norse maritime traditions recognize the importance of tidal timing for both fishing and raiding expeditions. Ancient harbour designs incorporated tidal considerations, with stone structures positioned to provide protection during high tide, while allowing access during low tide periods. Archaeological evidence from coastal settlements shows that human communities have been adapting to tidal rhythms for thousands of years. The development of mechanical tidal prediction machines in the 19th and early 20th centuries represents a fascinating intersection of astronomy, engineering, and practical navigation needs. These analog computers, built with brass gears and rotating drums, could mechanically calculate tidal predictions by simulating the orbital motions of celestial bodies. The most sophisticated of these machines incorporated dozens of tidal constituents, producing predictions that remained remarkably accurate well into the digital age. These mechanical marvels demonstrate humanity's persistent drive to understand and predict natural phenomena that affect daily life. The intricate clockwork mechanisms that drove tidal prediction machines mirror the celestial clockwork they were designed to simulate, creating mechanical analogies for gravitational forces operating across astronomical distances. The transition from mechanical to digital tidal prediction opened new possibilities for understanding the subtle influences that shape tidal patterns. Computer models can now incorporate thousands of variables and perform calculations that would have required months of work using mechanical methods. This computational power has revealed previously hidden patterns in tidal data and enabled predictions with accuracy that seemed impossible just decades ago. Satellite technology has revolutionized our ability to observe and understand tidal phenomena on a global scale. Radar altimetry satellites can measure ocean surface heights with precision measured in centimeters, creating detailed maps of tidal patterns across entire ocean basins. These satellite observations reveal the three-dimensional structure of tidal waves as they propagate across the world's oceans, showing how tidal energy flows from generation regions to dissipation areas. The global perspective provided by satellite observations has corrected many assumptions about tidal behavior that were based on limited coastal measurements. Ocean-wide tidal maps show that tidal patterns are far more complex than early theories suggested, with energy dissipation occurring in unexpected locations and tidal waves following paths that defy simple geometric predictions. These discoveries have implications for understanding energy dissipation in the Earth-Moon system and the long-term evolution of lunar distance. Tidal friction gradually slows Earth's rotation while transferring angular momentum to the Moon, causing our satellite to slowly spiral away from Earth. Precise measurements of tidal energy dissipation help scientists understand how quickly this process operates and what it means for the future of the Earth-Moon system. The Moon is currently receding from Earth at a rate of about 4 centimeters per year, roughly the same rate at which human fingernails grow. This seemingly insignificant change accumulates over geological time to create dramatic differences in tidal conditions. Fossil evidence preserved in ancient tidal deposits suggests that when the Moon was closer to Earth, tidal ranges may have exceeded anything we observe today. Future tidal conditions will gradually become less extreme as the Moon continues its slow retreat from Earth. Billions of years in the future, if Earth and the Moon both survive the Sun's eventual evolution into a red giant star, tidal ranges will be much smaller than they are today. The dynamic tidal environment that has shaped our planet's coastlines and influenced the evolution of life may represent a temporary phase in Earth's long history. But these far future considerations pale beside the immediate reality of tidal forces continuing to shape our world in countless subtle ways. Every grain of sand moved by tidal currents, every organism whose life cycle synchronizes with lunar rhythms, every human activity timed to work with rather than against tidal schedules participates in the ongoing story of gravitational forces that connect our planet to its celestial companion. The study of tidal phenomena continues to yield surprises that challenge our understanding of how gravitational forces operate in complex systems. Recent discoveries about tidal influences on atmospheric pressure, groundwater levels, and even seismic activity suggest that the Moon's gravitational reach extends into realms we are only beginning to explore. Advanced monitoring systems now detect tidal influences in phenomena as diverse as underground cave water levels, volcanic gas emissions, and the precise timing of avalanches in mountainous regions. These discoveries suggest that the Moon's gravitational influence permeates Earth's systems far more thoroughly than previously recognized, creating connections between celestial mechanics and terrestrial processes that operate across multiple scales of space and time. The implications of these discoveries extend beyond academic interest into practical applications for environmental monitoring, natural hazard prediction, and resource management. Understanding how tidal forces influence groundwater systems helps hydrologists predict water availability in coastal aquifers. Recognizing tidal influences on seismic activity may improve earthquake prediction models. Accounting for lunar effects on atmospheric pressure could enhance weather forecasting accuracy. Each new discovery reinforces the fundamental truth that Earth exists not as an isolated sphere floating in empty space, but as an active participant in a dynamic gravitational system where forces operating across vast distances create intimate connections between celestial motions and terrestrial phenomena, The moon's gentle but persistent pull on our oceans serves as a visible reminder of these hidden connections, a twice-daily demonstration of the invisible threads that bind our world to the larger cosmos. As our understanding of tidal forces deepens, we gain greater appreciation for the elegant complexity of the natural systems that sustain life on our planet. The same gravitational forces that move our oceans also help maintain the stable, orbital relationships that keep Earth in the habitable zone around our Sun. The tidal friction that gradually slows our planet's rotation also helps stabilize Earth's axial tilt, preventing dramatic climate variations that could make our world uninhabitable. These connections between tidal forces and planetary habitability suggest that the moon's influence on Earth extends far beyond the obvious effects of ocean tides. Our satellite companion may play a crucial role in maintaining the stable environmental conditions that have allowed complex life to evolve and flourish on our planet. The gentle tug of lunar gravity that moves our tides may be one of the hidden factors that makes Earth a uniquely suitable home for life as we know it. Tonight, as you prepare for sleep, the moon continues its ancient orbit, pulling at the waters of our world with mathematical precision that has never wavered throughout Earth's long history. The tides it creates connect us to forces that operate on scales both vast and intimate, reminding us that we are part of a universe where nothing exists in isolation, where every phenomenon emerges from relationships and connections that span the breadth of space and the depth of time. In the gentle rise and fall of tidal waters, we witness the visible expression of invisible forces that bind our world together, forces that demonstrate the profound unity underlying the apparent diversity of natural phenomena. The moon's gravitational embrace of our oceans speaks to something fundamental about the nature of existence itself, revealing that what appears separate and distinct is actually interconnected in ways that transcend our everyday understanding. The rhythm of the tides serves as a bridge between the human scale of experience and the cosmic scale of forces that shape our universe, offering us a daily reminder that we live not just on Earth, but in the cosmos itself, participants in a gravitational dance that began billions of years ago and will continue for billions of years to come. The precision with which we can predict these tidal rhythms reveals something profound about the mathematical nature of our universe. When you consult a tide table and see that high tide will occur at precisely 3:47 a.m. on a Tuesday 6 months from now, you're witnessing the result of calculations that trace their lineage back to Newton's laws of motion and universal gravitation. These predictions don't rely on guesswork or approximation, but emerge from the fundamental mathematical relationships that govern how massive objects interact across space. Modern tidal prediction involves harmonizing dozens of different periodic components, each representing a different aspect of the complex gravitational dance between Earth, Moon, and Sun. Scientists have identified over 300 distinct tidal constituents, each with its own period, amplitude, and phase relationship to the others. The principal lunar semi-diurnal constituent, known to tidal scientists as M2, dominates most tidal predictions with its 12-hour and 25-minute cycle. But dozens of other constituents add their own subtle influences, creating the unique tidal signature that characterizes each coastal location. The mathematical elegance of these tidal harmonics mirrors the harmonic series found in music and acoustics, suggesting deep connections between the rhythms that govern celestial mechanics and the mathematical patterns that underlie all wave phenomena. Just as a musical chord emerges from the combination of multiple individual frequencies, the complex tidal patterns we observe result from the superposition of numerous simple periodic functions, each representing a different gravitational influence. This mathematical approach to understanding tides has revealed patterns that span timescales far beyond human experience. The nodal cycle, an 18.5-year variation in tidal ranges caused by the slow precession of the Moon's orbital plane, creates long-term patterns that were recognized by ancient astronomers but only fully understood with the development of modern celestial mechanics. Coastal communities sometimes notice gradual changes in average tidal ranges over periods of years, not realizing they're witnessing the effects of orbital mechanics operating on generational timescales. Even longer cycles emerge from the intricate gravitational relationships within our solar system. The perigean spring tide cycle, occurring every 4 to 6 years when the Moon's closest approach to Earth coincides with spring tide conditions, creates exceptionally high tides that can surprise coastal residents who haven't experienced similar conditions in recent memory. These rare alignment events demonstrate how multiple periodic cycles can occasionally reinforce each other to create extreme conditions that exceed normal expectations. The study of historical tidal records reveals how these long-period variations have influenced human history in ways that participants at the time could not have understood. Coastal battles won or lost, exploration voyages that succeeded or failed, even the timing of major storms and their impacts on coastal communities often depended on tidal conditions influenced by celestial cycles operating far beyond human planning horizons. Archaeological evidence suggests that some ancient coastal structures were positioned with remarkable precision to work optimally during specific long-term tidal cycles, indicating that prehistoric engineers possessed sophisticated understanding of tidal patterns that spanned decades or centuries. Stone fish traps in Ireland and Wales show alignments that maximize their effectiveness during particular phases of the 18-year nodal cycle, suggesting that ancient builders planned their constructions with temporal horizons that extended far beyond individual human lifespans. The transmission of this tidal knowledge across generations required sophisticated oral traditions and observational practices that modern societies, with their reliance on written records and digital predictions, can barely comprehend. Traditional tidal calendars, encoded in cultural practices, seasonal ceremonies, and customary activities, preserved essential navigation and fishing knowledge through methods that integrated astronomical observation with practical coastal wisdom. Pacific Islander cultures developed particularly sophisticated systems for encoding tidal knowledge in navigational charts, ceremonial practices, and seasonal activities that preserve precise information about tidal patterns across vast ocean areas. These traditional knowledge systems often incorporated understanding of how tidal patterns varied between different island groups, seasonal changes in tidal timing and amplitude, and the relationships between tidal cycles and weather patterns that affected navigation safety. The accuracy of traditional tidal knowledge often exceeds modern scientific predictions for specific local conditions, particularly in areas where complex coastal geometry creates tidal patterns that defy simple mathematical modeling. Indigenous communities whose ancestors lived in the same coastal areas for hundreds or thousands of years developed empirical understanding of local tidal behavior that accounted for subtle influences that formal tidal theory struggles to capture. This traditional knowledge becomes increasingly valuable as climate change alters baseline conditions that affect how tidal patterns manifest in specific locations. Sea level rise changes the way tidal waves propagate through shallow coastal areas, while changing storm patterns affect the interaction between meteorological and astronomical tidal influences. Traditional observers who understand long-term natural variations can help distinguish between changes caused by climate shift and normal variations in tidal patterns. The integration of traditional tidal knowledge with modern scientific understanding creates opportunities for more accurate and culturally appropriate coastal management strategies. Community-based monitoring programs that combine traditional observation methods with scientific instruments often detect environmental changes more quickly and accurately than purely technical monitoring systems, particularly in remote areas where instrumental coverage is limited. Contemporary coastal engineering increasingly recognizes the value of designing infrastructure that works with natural tidal patterns rather than attempting to control or eliminate tidal influences entirely. Living shoreline projects use natural materials and processes to provide coastal protection while maintaining the tidal connections that sustain healthy coastal ecosystems. These approaches often prove more durable and cost-effective than hard engineering solutions that fight against natural tidal forces. The restoration of natural tidal patterns to areas where they have been disrupted by development represents one of the most challenging and rewarding applications of modern tidal science. Salt marsh restoration projects must carefully engineer tidal connections that provide appropriate flooding and drainage cycles while protecting adjacent developed areas from unwanted flooding. Success requires understanding not just the physical mechanics of tidal flow, but also the biological and chemical processes that depend on specific tidal timing and duration. Urban planning in coastal areas increasingly incorporates detailed tidal analysis to address challenges posed by more frequent flooding as sea levels rise and storm patterns change. Cities like Venice, Miami, and Bangkok are developing sophisticated tidal management systems that combine traditional flood control methods with advanced prediction systems and adaptive infrastructure designed to work with rather than against tidal forces. The economics of coastal development must now account for tidal influences that operate on multiple timescales, from daily flooding risks to long-term changes in tidal patterns caused by sea level rise and coastal evolution. Property values, insurance costs, and infrastructure investments all reflect growing awareness that coastal areas exist within dynamic tidal systems that will continue to change throughout the lifetime of human developments. Commercial shipping has evolved sophisticated systems for optimizing vessel movements to take advantage of favorable tidal conditions while minimizing delays and fuel costs. Modern port operations coordinate the movements of dozens of vessels simultaneously, timing arrivals and departures to maximize the use of tidal windows that provide adequate water depths for safe navigation. Container shipping schedules now incorporate tidal predictions made months in advance, creating global supply chain dependencies on astronomical calculations of extraordinary precision. The cruise industry has developed specialized expertise in tidal planning that allows massive passenger vessels to visit ports and anchorages that would otherwise be inaccessible. Shore excursion schedules must coordinate with tidal timing to ensure that tender operations can safely transport thousands of passengers between ships and shore during appropriate tidal conditions. The success of entire cruise itineraries often depends on tidal predictions that must account for seasonal variations and long-term cycles affecting destination ports. Fishing industries continue to rely heavily on tidal knowledge despite advances in fish-finding technology and GPS navigation. Many commercially important fish species show feeding and movement patterns closely tied to tidal cycles, with fishing success rates varying dramatically depending on tidal timing and current strength. Professional fishing operations often schedule their activities around tidal predictions that maximize catch rates while minimizing fuel costs and safety risks. Recreational fishing communities maintain rich traditions of tidal law that combines scientific understanding with empirical knowledge accumulated over generations of fishing experience. Local fishing guides develop expertise in reading subtle tidal influences that affect fish behavior in specific locations. Understanding how factors like water temperature, dissolved oxygen levels, and food availability interact with tidal cycles to create optimal fishing conditions. The growing popularity of coastal recreation activities has created new demands for accessible tidal information that serves casual users who may not understand the complexities of tidal prediction but need practical guidance for planning beach visits, kayaking trips, and tide pool exploration. Mobile applications now provide real-time tidal information with user-friendly interfaces that translate complex tidal data into simple recommendations for recreational activities. Educational programs designed to increase public understanding of tidal phenomena face the challenge of explaining concepts that operate on timescales and spatial scales far beyond typical human experience. Successful tidal education often relies on hands-on activities that allow participants to observe tidal changes directly while learning about the astronomical forces that drive these patterns. Citizen science projects focused on tidal monitoring engage coastal communities in collecting data that contributes to scientific understanding while building local knowledge about tidal patterns and their ecological importance. These programs often reveal local tidal phenomena that formal scientific monitoring systems miss, particularly in areas where complex coastal geometry creates unique tidal conditions. The artistic and cultural inspiration provided by tidal rhythms continues to influence human creativity in ways that reflect deep psychological connections to natural cycles. Composers have written symphonies that mirror tidal patterns, with musical structures that ebb and flow like ocean waters responding to lunar influence. Visual artists create works that capture the meditative quality of tidal transitions, using color, form, and movement to express the subtle majesty of water responding to celestial forces. Poetry and literature draw extensively on tidal imagery to explore themes of change, persistence, and the relationship between human consciousness and natural rhythms. The metaphorical richness of tidal language reflects intuitive understanding that tidal patterns represent something fundamental about the nature of existence itself, with their endless cycles of advance and retreat, building and release, presence and absence. Contemporary environmental art increasingly incorporates actual tidal movements into artistic installations that change with the rhythms of lunar gravity. These works create direct connections between human observers and astronomical forces, using the predictable yet ever-changing nature of tidal patterns to explore themes of time, change, and humanity's place within larger natural systems. The meditative qualities of tidal observation have inspired contemplative practices that use the rhythm of rising and falling waters as focuses for meditation and mindfulness. The slow, predictable pace of tidal change provides a natural timekeeper for reflective practices that help participants connect with natural rhythms, often obscured by the artificial timekeeping of modern life. Therapeutic applications of tidal awareness recognize that human physiology and psychology may retain connections to natural cycles that once played crucial roles in human evolution and survival. Some therapeutic approaches incorporate tidal timing into treatment schedules, recognizing that human circadian rhythms may be influenced by the same lunar cycles that drive tidal patterns. The future of human relationship with tidal forces will likely involve increasingly sophisticated integration of tidal knowledge into technological systems that enhance rather than replace human understanding of natural rhythms. Smart city technologies are tying tidal data into urban management, beginning to incorporate real systems that optimize everything from traffic flow to energy distribution based on tidal predictions. Climate adaptation strategies for coastal communities increasingly recognize that successful adaptation requires working with natural tidal patterns rather than attempting to eliminate tidal influences through engineering solutions alone. Green infrastructure approaches that incorporate tidal wetlands, living shorelines, and natural flood management systems often provide more resilient and cost-effective coastal protection than traditional hard engineering approaches. The development of tidal energy systems represents humanity's newest attempt to harness the power of lunar gravity for beneficial purposes, continuing a tradition that began with ancient tidal mills, but now operates at scales that could provide significant portions of global energy needs. Advanced tidal energy technologies are being designed to capture energy from tidal movements without disrupting the natural tidal processes that sustain coastal ecosystems. International cooperation in tidal research and management reflects growing recognition that tidal forces operate on scales that transcend political boundaries, requiring collaborative approaches to understanding and managing human interactions with tidal systems. Global tidal monitoring networks now provide real-time data that supports both scientific research and practical applications, ranging from navigation safety to climate monitoring. The scientific frontiers of tidal research continue to expand as new technologies enable observations and measurements that were impossible just decades ago. Underwater autonomous vehicles can now track tidal currents throughout entire tidal cycles, providing three-dimensional maps of how tidal energy moves through complex coastal environments. These detailed observations reveal phenomena that challenge existing theories about tidal behavior and open new possibilities for understanding how tidal forces shape marine ecosystems. Advanced computer modeling systems can now simulate tidal behavior with unprecedented accuracy and resolution, allowing researchers to explore how proposed coastal developments or climate changes might affect local and regional tidal patterns. These models help planners and engineers design projects that work with natural tidal forces while minimizing unintended consequences for coastal communities and ecosystems. The integration of artificial intelligence and machine learning techniques into tidal analysis is revealing patterns in tidal data that human researchers never noticed, identifying subtle correlations between tidal behavior and other environmental variables that may improve our understanding of how tidal systems respond to environmental change. As we stand at the threshold of an era where human activities increasingly influence global environmental systems, our relationship with tidal forces serves as a reminder that some natural phenomena operate according to principles that transcend human timescales and planning horizons. The moon that pulls so gently yet persistently at our oceans represents continuity with forces that shaped our planet long before human civilization emerged and will continue long after our current technological society has been transformed by changes we cannot yet imagine. The wisdom embedded in traditional tidal knowledge, the precision of modern scientific prediction, and the creative potential of emerging technologies all point toward possibilities for human relationship with tidal forces that honor both the practical needs of coastal communities and the deeper rhythms that connect our world to the larger cosmos. In learning to work with, rather than against the forces that move our tides, we participate in conversations between Earth and Moon that have been ongoing for billions of years, adding our voices to a dialogue that spans the gap between terrestrial and celestial scales of existence. The gentle persistence of tidal forces offers a model for human engagement with natural systems that emphasizes patience, observation, and adaptation rather than control and domination. As we face environmental challenges that require responses sustained over decades and centuries, the tidal model of persistent rhythmic influence operating on long timescales provides inspiration for approaches that work with natural systems, rather than attempting to overcome them through technological force alone. Tonight, as the moon continues its ancient journey across the sky, its gravitational influence reaches down to touch every molecule of water on our planet, creating movements and rhythms that connect the smallest tide pool to to the vastest ocean basin, linking the immediate experience of waves lapping at a beach to forces that operate across astronomical distances and geological time. In this connection between the intimate and the infinite, between the local and the cosmic, we find both humility and wonder at our place within systems far larger and more ancient than human civilization itself. The profound interconnectedness revealed by tidal forces extends into realms that challenge our most basic assumptions about the boundaries between living and non-living systems. Consider the extraordinary phenomenon of biological tidal clocks, internal timekeeping mechanisms that have evolved in countless organisms to synchronize their life processes with the rhythm of lunar gravity. These biological clocks operate with such precision that they continue to function even when organisms are removed from tidal environments entirely, suggesting that the influence of celestial mechanics has become encoded in the very fabric of life itself. Marine creatures demonstrate the most obvious examples of these biological tidal rhythms. Certain species of marine worms emerge from their burrows to reproduce only during specific tidal conditions, timing their spawning with mathematical precision that rivals human-made chronometers. The pololo worm of the Pacific, for instance, swarms to the surface for reproduction during the third quarter moon of October and November, creating spectacular displays that local communities have celebrated for centuries. The timing is so reliable that entire cultural festivals have developed around these predictable biological events. But perhaps even more remarkable are the organisms that maintain tidal rhythms far from any ocean influence. Researchers have discovered that certain coastal plants continue to exhibit tidal patterns in their metabolic activity when transplanted to inland locations hundreds of miles from the sea. Their cellular processes still pulse with 12-hour cycles that match the tidal rhythms of their ancestral coastal habitats, as if the moon's gravitational influence had become permanently impressed into their genetic programming. Oysters provide one of the most studied examples of biological tidal clocks. When transported from their native waters to inland laboratories, these mollusks initially continue opening and closing their shells according to the tidal schedule of their home waters. But over time, something even more fascinating occurs. The oysters gradually shift their rhythm to match what the tidal schedule would be if their new location were somehow connected to the ocean. They begin responding not to the actual tides they once experienced, but to the hypothetical tidal forces that would exist at their current location if lunar gravity could reach them through solid Earth. This suggests that these creatures possess an internal sensitivity to gravitational forces themselves, not just to the secondary effects of those forces on water movement. Their biological clocks may be directly influenced by the same lunar gravitational field that moves our oceans, implying a level of interconnection between life and celestial mechanics that we are only beginning to understand. Fiddler crabs demonstrate similarly remarkable tidal synchronization. These small crustaceans emerge from their burrows to feed during low tide with such regularity that researchers can predict their behavior months in advance using astronomical calculations. When transported to constant laboratory conditions with no external tidal cues, rhythmic activity crabs continue their patterns for weeks. Their internal clocks maintaining synchronization with tidal cycles they can no longer directly experience. Even more intriguingly, some fiddler crab populations show slight variations in their tidal rhythms that correspond precisely to the unique tidal patterns of their specific home beaches. Crabs from different locations maintain subtly different internal clock settings that reflect the particular tidal characteristics of their native habitats, suggesting that biological tidal clocks can be fine-tuned to local gravitational conditions with extraordinary precision. Birds that feed in tidal environments have evolved behavioral patterns that integrate tidal timing with other environmental cues in ways that maximize their foraging efficiency. Shorebirds like sandpipers and plovers time their feeding activities to coincide with the peak abundance of invertebrate prey that emerges during specific tidal conditions. Their migration schedules often align with seasonal tidal patterns that provide optimal feeding opportunities at stopover sites along their flyways. The Arctic tern, that remarkable bird that experiences 2 summers each year by migrating between polar regions, times its movements partly around tidal conditions that affect food availability at crucial refueling stops. These birds demonstrate how tidal influences can shape life patterns that span continents and integrate with other environmental cycles operating on vastly different scales. Human physiology may retain subtle connections to tidal rhythms that reflect our evolutionary history in coastal environments. Some researchers have noted correlations between lunar cycles and various biological processes, though the mechanisms behind these potential connections remain poorly understood. Sleep patterns, hormone cycles, and even wound healing rates show statistical associations with lunar phases that suggest possible remnants of ancient biological tidal clocks. The human menstrual cycle, averaging 28 days, remarkably closely matches the lunar month, leading some researchers to speculate about possible evolutionary connections between human reproductive timing and celestial cycles. While definitive scientific proof remains elusive, the statistical correlation has intrigued researchers for generations and continues to inspire studies into the possible influence of lunar cycles on human biology. Emergency room personnel and law enforcement officers often report anecdotal observations of increased activity during full moon periods, though rigorous scientific studies have found mixed results when attempting to document these patterns statistically. The persistence of these observations across different cultures and professions suggests that the relationship between lunar cycles and human behavior may be more complex than simple statistical analysis can reveal. The field of chronobiology, which studies biological rhythms, has revealed that living organisms operate according to multiple internal clocks that synchronize with different environmental cycles. Circadian rhythms, synchronized to the 24-hour solar day, are well understood and widely recognized. But growing evidence suggests that circadian rhythms, synchronized to the 12.5-hour tidal cycle, may also play important roles in biological timing systems. These biological tidal clocks appear to operate independently of circadian clocks, suggesting that organisms possess multiple internal timekeeping systems that can simultaneously track different environmental rhythms. The interaction between these different biological clocks creates complex patterns of activity and rest that reflect the multiple periodic influences operating in natural environments. Research into biological tidal rhythms has practical applications for aquaculture operations that seek to optimize feeding schedules and harvest timing to align with natural biological rhythms. Fish and shellfish often show improved growth rates and survival when their care schedules synchronize with their internal tidal clocks, suggesting that understanding these rhythms can improve both the efficiency and welfare of aquaculture systems. Medical research has begun exploring whether human healing processes might be influenced by tidal or lunar cycles, particularly for patients whose conditions involve fluid balance or circulation issues. While results remain preliminary, some studies suggest that surgical outcomes and recovery rates may show subtle correlations with lunar phases, potentially reflecting ancient biological connections to celestial rhythms. The pharmaceutical industry has shown interest in chronotherapy, the practice of timing drug administration to align with natural biological rhythms. Understanding how tidal rhythms might influence drug metabolism and effectiveness could lead to more precise treatment protocols that account for multiple biological timekeeping systems simultaneously. Agricultural applications of tidal rhythm research focus on coastal farming systems, where soil salinity and water availability fluctuate with tidal cycles. Some coastal crops show improved yields when planting and harvesting schedules align with tidal patterns that optimize soil conditions and nutrient availability. Traditional farming practices in tidal areas often incorporated this knowledge, though the scientific understanding of underlying mechanisms has only recently begun to catch up with empirical observations. Ecosystem restoration projects increasingly recognize the importance of understanding biological tidal rhythms when designing interventions in coastal environments. Restoration success often depends on timing activities to align with the natural rhythms of target species, whether for fish passage projects that must coordinate with spawning migrations, or wetland plantings that must synchronize with tidal exposure cycles. The study of biological tidal clocks also provides insights into how organisms might adapt to climate change and shifting environmental conditions. As sea level rise alters tidal patterns in coastal environments, species with strong tidal rhythm dependencies may need to adjust their internal clocks to maintain synchronization with changing environmental conditions. Some organisms demonstrate remarkable flexibility in their tidal clock settings, adjusting to new tidal conditions within days or weeks of being moved to different environments. Others appear more rigidly programmed, maintaining ancestral tidal rhythms even when environmental conditions change. Understanding these differences in biological flexibility helps predict which species may be most vulnerable to environmental changes that alter tidal patterns. Evolutionary biologists are fascinated by the mechanisms through which gravitational forces became incorporated into biological timing systems. The evolution of tidal clocks represents a remarkable example of how life has learned to synchronize with cosmic forces, transforming astronomical influences into biological advantages that enhance survival and reproduction. The molecular mechanisms underlying biological tidal clocks are gradually being revealed through advances in genetic research and biochemical analysis. Scientists have identified specific genes and proteins that appear to be involved in tidal timekeeping, though the complete picture of how cellular processes translate gravitational influences into biological rhythms remains an active area of research. Comparative studies of tidal clock mechanisms across different species reveal both common principles and remarkable diversity in how organisms have solved the challenge of keeping time with celestial cycles. Some species use simple biochemical oscillators, while others employ complex networks of interacting cellular clocks that can maintain synchronization with multiple environmental rhythms simultaneously. The precision of biological tidal clocks often exceeds what would be necessary for survival in most environments, suggesting that these timing systems may have evolved not just for immediate adaptive advantages, but also for long-term synchronization with environmental patterns that operate across multiple generations. This long-term perspective in biological timing systems reflects the persistence of tidal influences across evolutionary timescales. Disruptions to biological tidal rhythms can have cascading effects throughout ecosystems as the precise timing relationships between different species become desynchronized. Light pollution, noise pollution, and other human influences on coastal environments can interfere with the environmental cues that biological tidal clocks use for synchronization, potentially disrupting ecological relationships that have been stable for thousands of years. Conservation biology increasingly recognizes the importance of protecting not just habitat areas, but also the natural rhythm patterns that maintain ecosystem function. Protecting tidal rhythms requires understanding and minimizing human activities that disrupt the subtle environmental cues upon which biological tidal clocks depend. The remarkable precision and persistence of biological tidal clocks provides inspiration for human-designed timing systems that must operate reliably in challenging environments. Engineers studying biological chronometers are developing new approaches to timekeeping that could improve the reliability of navigation systems, communication networks, and other technologies that require precise timing coordination. Biomimetic research into tidal clock mechanisms may lead to new types of sensors that can detect gravitational influences or other subtle environmental changes with the sensitivity demonstrated by living organisms. These biological sensors often outperform technological alternatives in terms of sensitivity, reliability, and energy efficiency. The integration of biological tidal rhythm research with technological applications represents a growing field that seeks to learn from billions of years of evolutionary optimization in biological timing systems. Understanding how living organisms achieve such precise synchronization with celestial cycles could inform the design of artificial systems that need to maintain long-term coordination with natural rhythms. As we deepen our understanding of biological tidal clocks, we gain greater appreciation for the profound interconnectedness between life and the cosmic forces that shape our world. These biological timing systems represent more than mere adaptations to environmental conditions. They embody a fundamental integration between living processes and the gravitational dance of celestial bodies. The existence of biological tidal clocks suggests that the boundary between living and non-living systems may be less distinct than we typically assume. When organisms carry within their cellular machinery the rhythmic signatures of lunar gravity, they become living expressions of cosmic forces, biological embodiments of astronomical principles operating on scales that span from molecular processes to planetary motions. This integration of cosmic and biological rhythms points toward a universe where consciousness and physical forces participate in relationships that transcend traditional scientific categories. The moon's gravitational influence on our tides becomes not just a physical phenomenon, but a connecting principle that links the motion of celestial bodies to the rhythms of life itself. In the gentle, we find evidence that life persistence of biological tidal clocks and cosmos are not separate realms, but aspects of a unified system where astronomical forces express themselves through biological processes, creating patterns of connection that bridge the gap between the physics of planetary motion and the chemistry of living cells. These connections remind us that we exist not as isolated beings in an indifferent universe, but as conscious participants in a cosmic community where gravitational forces and biological rhythms dance together in patterns of exquisite complexity and beauty. The tidal forces that move our oceans thus become visible expressions of deeper connections that permeate all aspects of existence, linking the rhythms of our hearts to the orbital dance of moon and earth, connecting the cycles of life to the eternal choreography of celestial mechanics that has been unfolding since the first moments of cosmic time. The story of how the moon moves our tides reveals something even more profound when we consider the extraordinary delicacy of the forces involved. If you were to hold a single drop of water in your palm and imagine the moon trying to lift it, the gravitational force would be so weak that it wouldn't overcome even the surface tension holding that droplet together. Yet somehow, across the vast scales of our oceans, these infinitesimal tugs accumulate into movements of water that dwarf anything human engineering has ever accomplished. This accumulation of seemingly insignificant forces into globally significant phenomena speaks to something fundamental about how nature operates. The ocean responds to lunar gravity not because any individual molecule of water experiences a strong pull, but because billions upon billions of molecules all experience the same gentle influence simultaneously. It's like a vast choir where each voice contributes only a whisper, yet together they create a sound that can be heard across continents. The mathematics of this accumulation reveals patterns that connect the smallest scales of molecular interaction to the largest scales of planetary motion. When we trace how tidal forces propagate through ocean basins, we discover that the same principles governing wave mechanics in a bathtub also govern the movement of water masses larger than entire continents. The physics remains consistent across these enormous differences in scale, creating a kind of mathematical poetry, where the same equations describe phenomena ranging from ripples in a pond to the circulation of entire ocean systems. But perhaps the most remarkable aspect of tidal mechanics is how these forces manage to coordinate the behavior of water across such vast distances with such extraordinary precision. Consider that high tide occurs nearly simultaneously along thousands of miles of coastline, despite the complex topography of ocean floors and the countless obstacles that might be expected to disrupt this coordination. The Moon's gravitational field creates what physicists call a forcing function that synchronizes water movement across entire ocean basins with the reliability of a cosmic metronome. This synchronization occurs because tidal forces operate through the fabric of space itself, reaching every part of our planet simultaneously rather than propagating as signals that travel at finite speeds. Unlike sound waves or light waves, which must travel from source to destination, gravitational influences permeate space instantaneously according to our current understanding of physics. The Moon's position creates a gravitational field configuration that extends throughout the Earth-Moon system, influencing every point within that field according to precise mathematical relationships that depend only on mass and distance. The instantaneous nature of gravitational influence means that as the Moon moves in its orbit, the tidal force pattern moves with it, creating a constantly shifting gravitational landscape that ocean waters must continuously adjust to match. This creates the dynamic character of tidal systems, where the equilibrium position for ocean surfaces changes continuously as celestial bodies move through their orbital dance. Ocean waters never quite achieve perfect equilibrium with the instantaneous gravitational force pattern because the inertia of moving water masses prevents instantaneous adjustment to changing conditions. This lag between the gravitational forcing and the ocean's response creates what oceanographers call tidal currents. The horizontal flows of water that transport the enormous volumes needed to create the vertical changes we observe as rising and falling water levels. These tidal currents represent some of the most powerful forces moving across our planet's surface. In narrow straits and channels where vast volumes of water must flow through restricted passages, tidal currents can exceed the speed of the fastest rivers, creating whirlpools, standing waves, and other dramatic phenomena that demonstrate the immense energies involved in tidal movements. The Strait of Corryvreckan between Scottish islands creates a whirlpool during spring tides that can be heard from miles away as billions of gallons of water funnel through the narrow passage with such force that the turbulence extends hundreds of feet into the air. Similar phenomena occur wherever tidal flows encounter restrictions that concentrate the energy of moving water into spectacular displays of natural hydraulic power. These concentrated expressions of tidal energy reveal something important about the total energy budget involved in global tidal systems. The energy required to move the world's oceans twice each day represents one of the largest energy transfers occurring on our planet, comparable to the energy output of thousands of power plants operating continuously. This energy comes ultimately from the rotational energy of the Earth-Moon system, gradually extracted through tidal friction that slowly changes the orbital characteristics of both bodies. The extraction of rotational energy through tidal friction creates one of the most subtle yet profound long-term consequences of tidal forces. Each tidal cycle removes a tiny amount of energy from Earth's rotation, gradually lengthening our days, while simultaneously transferring that energy to the Moon's orbital motion, causing our satellite to slowly spiral outward. This energy transfer has been operating for billions of years, fundamentally shaping the evolution of the Earth-Moon system. Geological evidence preserved in ancient tidal deposits suggests that early in Earth's history, when the Moon orbited much closer to our planet, days were significantly shorter and tidal ranges were dramatically larger than anything we experience today. Some researchers estimate that tidal ranges may have exceeded 1,000 feet during certain periods, creating coastal environments so dynamic that they may have played crucial roles in the chemical processes that gave rise to life itself. The gradual slowing of Earth's rotation due to tidal friction has implications that extend far beyond changes in day length. Earth's rotation rate influences atmospheric circulation patterns, ocean current systems, and even the planet's magnetic field generation. The progressive lengthening of days over geological time has required continuous adaptation by climate systems and biological processes that depend on diurnal rhythms. Weather patterns show subtle but measurable correlations with tidal cycles that reflect the complex interactions between lunar gravity and atmospheric dynamics. While the atmosphere is far less responsive to tidal forces than liquid water, the enormous scale of atmospheric systems allows even tiny tidal influences to accumulate into detectable effects on pressure patterns, wind systems, and storm development. The jet stream, that high-altitude river of air that guides weather systems across continents, shows slight but statistically significant variations that correlate with lunar position and tidal cycles. These correlations are so subtle that they were only discovered through sophisticated statistical analysis of decades of weather data, yet they represent genuine physical connections between celestial mechanics and terrestrial weather patterns. Hurricane and typhoon development occasionally shows timing correlations with tidal cycles, particularly during periods when other atmospheric conditions are marginally favorable for storm formation. The additional atmospheric disturbance created by tidal forces may provide just enough extra energy to tip marginal conditions towards storm development, demonstrating how tiny influences can have disproportionately large consequences in complex systems. Atmospheric tides also influence the behavior of radio waves and satellite communications by creating subtle variations in the density and electrical properties of the upper atmosphere. These effects are so small that they're typically overwhelmed by solar influences. But during periods of low solar activity, lunar atmospheric tides become detectable and must be accounted for in precision navigation and communication systems. The study of atmospheric tides has revealed unexpected connections between lunar position and phenomena as diverse as lightning frequency, aurora activity, and even the behavior of migrating birds that navigate using magnetic field variations influenced by atmospheric electrical changes. These discoveries continue to expand our understanding of how gravitational forces propagate their influence through interconnected natural systems. Seismic activity shows statistical correlations with tidal cycles that suggest the Moon's gravitational influence may affect the timing of earthquakes and volcanic eruptions. While tidal forces are far too weak to cause these geological events, they may influence the precise timing of events that are already approaching critical thresholds due to longer-term geological processes. The additional stress imposed by tidal forces on fault systems and magma chambers represents only a tiny fraction of the total stress involved in geological processes. But this tiny additional stress may be sufficient to trigger events that were already on the verge of occurring. This makes tidal influences on seismic activity difficult to predict or quantify, since they depend on the pre-existing stress conditions that vary dramatically between different geological settings. Underground fluid systems, including oil reservoirs, geothermal systems, and groundwater aquifers, respond to tidal forces in ways that affect everything from well productivity to earthquake triggering. The compression and expansion of underground formations under tidal stress creates pressure variations that can influence fluid flow rates and the mechanical stability of underground structures. Mining operations in some locations must account for tidal influences on ground stability and groundwater levels. Deep mines occasionally experience flooding or structural problems that correlate with tidal cycles, as the subtle flexing of Earth's crust under lunar gravity affects underground water flow patterns and rock stability. The precision required to detect and measure these subtle tidal influences on solid Earth phenomena has driven the development of increasingly sensitive scientific instruments. Modern gravimeters can detect variations in gravitational acceleration smaller than 1 part in a billion, revealing the detailed structure of tidal forces as they propagate through Earth's interior. These ultra-sensitive measurements have revealed that Earth's response to tidal forces is more complex than early theories predicted. Different types of seismic waves propagate through our planet at different speeds, creating a situation where various parts of Earth's interior respond to lunar gravity with slightly different timing and amplitude patterns. The study of these internal tidal responses provides insights into Earth's deep structure that complement information obtained through earthquake seismology. Tidal analysis reveals details about the density, elasticity, and fluid content of Earth's interior that help scientists understand processes operating in regions that will never be directly accessible to human observation. Ocean floor spreading and continental drift occur on timescales so long that tidal influences represent only tiny perturbations to these massive geological processes. However, the cumulative effect of billions of years of tidal stress cycling may have influenced the patterns of crustal evolution and the locations where major geological features developed. Some researchers have speculated that the regular stress cycling imposed by tidal forces may have influenced the development of life by creating chemical concentration gradients and energy sources that wouldn't exist in a tidally locked system. The periodic exposure and submersion of coastal areas creates unique chemical environments where complex organic molecules might have formed and evolved. The role of tidal forces in early Earth's history remains an active area of research, with implications for understanding both the origin of life on our planet and the potential for life on other worlds that experience strong tidal influences. Moons of Jupiter and Saturn that experience extreme tidal heating from their giant planet hosts may harbor subsurface oceans where similar processes could operate. Tidal heating on these distant moons creates internal energy sources that could maintain liquid water and drive chemical processes even in the absence of solar energy. The same gravitational forces that create our familiar ocean tides may be sustaining entirely different types of aquatic environments in the outer solar system, hidden beneath kilometers of ice, but potentially teeming with exotic forms of life. The universality of tidal forces throughout the cosmos means that the principles governing Earth's tidal systems apply wherever gravitational bodies interact. Binary star systems experience tidal forces that can distort stellar shapes and influence stellar evolution. Planetary systems with closely orbiting worlds experience tidal effects that can synchronize rotational periods and orbital characteristics. The study of tidal phenomena on Earth provides a foundation for understanding similar processes throughout the universe, connecting our local experience of rising and falling waters to fundamental principles of celestial mechanics that operate on scales ranging from asteroid systems to galaxy clusters. As space exploration advances and we begin to study other worlds directly, the knowledge gained from understanding Earth's tidal systems will prove invaluable for interpreting observations of tidal phenomena on exoplanets, moons, and other celestial bodies. The mathematical frameworks developed to predict Earth's tides can be adapted to analyze tidal systems operating under different gravitational conditions and with different physical parameters. Future human settlements on other worlds will need to understand and work with local tidal conditions, whether they involve traditional liquid tides, atmospheric tides, or exotic phenomena like tidal heating in subsurface oceans. The principles learned from millennia of human interaction with Earth's tidal systems will inform how we adapt to gravitational environments that may be profoundly different from our home planet. The technology being developed to harness Earth's tidal energy could potentially be adapted for use on other worlds where tidal forces operate under different conditions, but according to the same fundamental physical principles. Tidal energy systems designed for Mars moons or the satellites of gas giant planets might operate on completely different scales, but would rely on the same basic understanding of how gravitational forces create predictable energy flows. As our understanding of tidal systems deepens, we gain greater appreciation for the elegant simplicity underlying phenomena of extraordinary complexity. The moon's gentle but persistent gravitational embrace of our planet creates a symphony of interconnected responses that span from molecular scale processes to global scale circulation patterns, all orchestrated by mathematical relationships of remarkable beauty and precision. The rhythm of the tides serves as a constant reminder that we inhabit a dynamic universe where nothing remains static, where even the most massive and seemingly permanent features of our world participate in ongoing dances of change and adaptation. The ocean waters that rise and fall in response to lunar gravity connect us to processes that began before our solar system formed and will continue long after our sun has evolved beyond recognition. In the end, the story of how the moon moves our tides reveals something profound about the nature of influence itself. Forces that seem impossibly subtle when considered individually can accumulate into phenomena of planetary significance when they operate consistently across vast scales of space and time. The moon's gravitational whisper becomes Earth's oceanic symphony through the patient accumulation of countless tiny influences into patterns of motion that shape coastlines, guide navigation, and regulate the rhythms of life itself. Tonight, as you rest in the quiet comfort of your evening, remember that above you, the moon continues its ancient orbital dance, pulling gently but persistently at every drop of water on our planet. That pull connects you to forces that operate across scales from the quantum to the cosmic, reminding you that you exist not in isolation, but as part of a universe where the smallest influences can create the largest consequences, where patience and persistence can move oceans, and where the gentle rhythm of tidal forces continues to write the story of our world in patterns of water and time that stretch from the deepest past toward an infinite future. The tides will continue their eternal dance long after human civilization has transformed into something we cannot yet imagine, carrying forward the memory of gravitational conversations between worlds, preserving in their endless rhythm the mathematical poetry of celestial mechanics, made manifest in the patient rise and fall of waters that connect every shoreline to the cosmic clockwork of the heavens themselves. In this vast oceanic symphony, we encounter something that might surprise you about the very nature of water itself. While we often think of the ocean as a single, unified body of water, tidal forces reveal that our seas are actually composed of countless distinct water masses, each with its own density, temperature, and chemical signature. These water masses respond to lunar gravity not as a homogeneous fluid, but as layers upon layers of liquid communities, each dancing to the moon's gravitational music in its own unique way. Deep ocean waters, cold and dense from their polar origins, move differently under tidal influence than the warm surface waters that have absorbed tropical sunshine for months or years. The boundary layers between these water masses create invisible highways in the sea, channels where tidal energy flows with particular intensity, mixing nutrients and heat in patterns that would be impossible without the moon's persistent gravitational choreography. Consider the remarkable phenomenon of internal tides, waves that move not at the surface where we can see them, but deep within the ocean's interior. These invisible giants can tower hundreds of meters high, moving along the boundaries between different water masses like underwater mountains in slow motion. They carry enormous amounts of energy across entire ocean basins, yet remain completely hidden from surface observation. These internal waves demonstrate something profound about the three-dimensional nature of tidal forces. While we experience tides primarily as vertical changes in water level, the ocean responds to lunar gravity as a complex, layered system where horizontal movements can be just as important as vertical ones. Vast underwater rivers flow beneath the surface, carrying water masses thousands of miles from their origins, all driven by the subtle gravitational gradients created by our orbiting companion. The interaction between these internal tidal currents and underwater mountain ranges creates some of the ocean's most dramatic hidden phenomena. When deep tidal flows encounter seamounts and underwater ridges, they generate turbulence so intense it can mix water masses that would otherwise remain separate for centuries. This deep ocean mixing plays a crucial role in global climate regulation, bringing nutrients to the surface and distributing heat throughout the world's oceans. Oceanographers have discovered that much of the energy that drives global ocean circulation ultimately traces back to tidal mixing processes operating in the deep sea. Without the moon's gravitational stirring of these deep waters, our oceans would stratify into layers that rarely interact, fundamentally altering Earth's climate system and making our planet far less hospitable to life as we know it. The biological implications of this deep tidal mixing extend throughout marine ecosystems in ways that scientists are still discovering. Many of the nutrients that support ocean productivity are recycled through deep water processes driven by tidal energy. Microscopic organisms that form the base of marine food webs depend on this tidal mixing to bring essential minerals from the ocean depths to the sunlit waters where photosynthesis can occur. Even the oxygen content of deep ocean waters depends partly on tidal mixing processes that circulate oxygen-rich surface waters downward while bringing nutrient-rich deep waters toward the surface. Without this tidal ventilation system, large portions of the ocean would become oxygen-depleted dead zones, incapable of supporting complex marine life. Tonight, as you rest in the gentle embrace of sleep, the moon continues its ancient orbital dance, pulling at the waters of our world with the same patient persistence it has shown for billions of years. In understanding how this celestial companion moves our tides, we've discovered something profound about the interconnected nature of existence itself. From the smallest molecule of water responding to gravitational whispers to the vast biological clocks that pulse within countless creatures, we've witnessed how cosmic forces weave themselves into the very fabric of life on Earth. The tides that rise and fall outside your window carry within them the mathematical poetry of planetary motion, the accumulated wisdom of ancient navigators, and the promise of sustainable energy for generations yet to come. Sweet dreams, fellow traveler in this cosmic dance,